In this video, we explore the controversial world of geoengineering and its potential role in combating climate change. As global temperatures rise and climate impacts intensify, some scientists are advocating for techniques that could manipulate the Earth's environment. We'll delve into the different types of geoengineering, focusing on solar radiation management and carbon dioxide removal, while weighing the potential benefits against the risks and uncertainties they pose. Additionally, we'll examine the ethical dilemmas and governance challenges surrounding these technologies, asking the critical question: is geoengineering a viable solution or a dangerous gamble? 1. Types of geoengineering. Geoengineering is broadly categorized into two main types: solar radiation management, SRM, and carbon dioxide removal, CDR. SRM aims to reflect sunlight away from the Earth, thus reducing the amount of heat trapped by the atmosphere. On the other hand, CDR focuses on removing carbon dioxide from the atmosphere, thereby reducing the greenhouse effect. Both approaches have their own potential benefits and risks, making them subjects of intense debate and scrutiny. 2. Solar radiation management, SRM. One of the most discussed techniques under SRM is stratospheric aerosol injection. This method involves spraying tiny reflective particles into the upper atmosphere to cool the planet by reflecting sunlight back into space. The idea is similar to how volcanic eruptions can lead to temporary cooling by injecting ash and sulfur dioxide into the stratosphere. While the concept sounds promising, it remains largely theoretical and is fraught with uncertainties, such as how these particles might affect weather patterns and ecosystems. 3. Carbon dioxide removal, CDR. CDR encompasses a variety of methods, each with its own approach to capturing and storing CO2. Afforestation, for example, involves planting trees to absorb CO2 through photosynthesis. Ocean fertilization aims to increase the growth of phytoplankton, which can also capture CO2. Direct air capture technology is another innovative approach that involves machines that extract CO2 directly from the air. Despite their potential, these methods face challenges related to scalability, cost, and effectiveness. 4. Potential benefits. Geoengineering could theoretically offer significant benefits in the fight against climate change. By reducing global temperatures, it might help mitigate the impacts of extreme weather events, sea level rise, and loss of biodiversity. Additionally, it could provide valuable time for societies to transition to sustainable energy systems. However, these benefits remain speculative until more research can determine the feasibility and safety of geoengineering techniques. 5. Risks and uncertainties. The potential risks and uncertainties associated with geoengineering are significant. For instance, altering the Earth's climate systems could have unintended consequences, such as disrupting weather patterns or affecting rainfall distribution. Moreover, the implementation of geoengineering could lead to geopolitical tensions, as nations might disagree on how these technologies should be deployed or who should have control over them. These risks highlight the need for cautious exploration and thorough understanding before any large-scale implementation. 6. Moral hazard. A significant concern with geoengineering is the moral hazard it presents. There is a worry that reliance on these technologies might reduce the urgency to cut greenhouse gas emissions. If geoengineering is seen as a quick fix, it could lead to continued reliance on fossil fuels and delay necessary climate actions. This could ultimately hinder global efforts to achieve a sustainable and low-carbon future. 7. Ethical considerations. The deployment of geoengineering raises profound ethical questions. Who should control these powerful technologies, and who should bear the risks? How can we ensure fair and equitable global governance over geoengineering efforts? These questions require careful consideration and international collaboration to ensure that the deployment of geoengineering does not exacerbate existing inequalities or create new ones. 8. Technological challenges. Many geoengineering methods are still in the experimental stage, facing significant technological and logistical hurdles to large-scale implementation. For example, the technology for direct air capture is still developing and currently operates at a high cost. Similarly, the long-term effects of techniques like ocean fertilization remain largely unknown. Overcoming these challenges will require substantial investment in research and development, as well as robust regulatory frameworks to ensure safety and efficacy. 9. International governance. Currently, there is no comprehensive international framework regulating geoengineering. However, discussions are ongoing within the United Nations and other global bodies about how to manage and oversee its research and potential deployment. Creating a robust international governance system will be crucial to ensure that geoengineering is used responsibly and equitably, avoiding potential conflicts and ensuring that its benefits are shared globally.